Hello everyone, welcome back to our lecture series of complex analysis. In this lecture, we will study the complex trigonometric functions. The trigonometric functions like sine x, cosec x, tan x, cot x, sec x इस तरीके के ट्रिग्नोमेट्रिक फंक्शंस आप ऑलरेडी रियल आंसर्स में पढ़ चुके हैं जहां पर x वाज अ रियल वेरिएबल. अब इन सभी ट्रिग्नोमेट्रिक फंक्शंस को हम एक कॉम्प्लेक्स वेरिएबल के लिए इस लेक्चर में डिस्कस करने वाले हैं. So let us start the discussion that whenever we have x is a real variable, then from Euler's formula we have this identity, that is e to the power iota x, that is equals to cos x plus iota sin x. Okay, let me call this as 1. And same time, if we have e to the power minus iota x, then this will be equals to cos x minus iota sin x. Okay, here this x is a real variable, right? अब अगर हम यहाँ से cos और sin को आइडेंटिफाई करें, then you can see the cos function can be given as cos x will be equals to the addition, और जब हम ऐड करेंगे and then we can divide by 2, so we will have e to the power iota x plus e to the power minus iota x over 2, and you can have the sin x also. Sin x will be equals to e to the power iota x minus e to the power minus iota x over 2 iota, right? Let me call this as equation number 3 and this is as equation number 4. Now look at the equation number 3 and 4. ये दोनों इक्वेशन हमें सजेस्ट करते हैं कि जिस तरीके से हमने रियल वेरिएबल x के लिए cos और sin फंक्शन को डिफाइन किया है in the form of exponential function, and this exponential function is the complex exponential function now. So you have a relation between the real trigonometric function and the complex exponential function. So by the presence of this complex exponential functions in these two expressions, these two equations, third and fourth, suggest us that we can define the cos and sine function for the complex variable in a similar manner. Okay, so this will provide us the definition of sine and cos function for the complex variable, and let me write that definition. We will just replace this x only. Okay, so definition, and this definition will define the complex sine and cosine function. Okay, so the sine and cosine functions for complex variable z are defined by, you can see we can define it as sin z. जैसे हमने sin x को डिफाइन किया था, we are going to just replace x by z only. Okay, we will have e to the power iota z minus e to the power minus iota z over 2 iota, and same time we have cos z is equal to e to the power iota z plus e to the power minus iota z over 2. Let me call this equation number 5 and this is equation number 6. So this is the definition of sine and cosine function. And the moment you have sine and cosine function using the relation between other trigonometric functions, you can write the expression for sine and tan, cot, sec and cosec function. Okay, so let me write that other trigonometric functions. So you can define like we have tangent is equal to sine z over cos z. Okay, then we have cot z is equal to cos z or sine z. Okay, now if you want to find the definition of tangent and cot z, so just replace this sine z by e to the power iota z minus e to the power minus iota z over 2 iota, and the same expression for the cos z. So you will have the expression for tangent in form of complex exponential function. Okay, and the function sec z can be given by 1 over cot z, and same time for the and cosec z is equal to 1 over sine z. Okay, let us call these equations as equation number 7. ठीक है, so whenever we refer equation number 7, that means we are talking one of these formulas. Okay, now let me identify some identities which are like जैसे कि हमने पढ़ा था sin square x plus cos square x is always equal to 1. Then we have sin minus x equal to minus sin x, then cos minus x equal to cos x. इस तरीके की जितनी भी entities है in the real analysis, they these are also true in the complex analysis. Okay, so some identities. Some identities. Okay, so let me write that most of the familiar identities for real trigonometric functions hold for complex trigonometric functions. As you can see, जैसे कि अगर मैं बात करूं सबसे पहले, you can see if I talk about the first identity, then you can see if I want to identify what is sine minus z. Okay, so you can see by the formula I just need to replace z by minus z only. Okay, so it will be equals to iota minus z and minus e to the power minus iota minus z over 2 iota, right? And if we simplify this, then we will have e to the power minus iota z minus e to the power, it will be plus iota z over 2 iota, and we can write this as e to the power minus e to the power iota z minus e to the power minus iota z over 2 iota, and we know this expression is for sin z, so we can write minus sin z. ओके, सो ये सिमिलर आइडेंटिटी हमें रियल वेरिएबल के लिए भी मिलती है. सो साइन माइनस जेड इज माइनस साइन जेड, एंड इन अ सिमिलर मैनर यू कैन राइट द कोस माइनस जेड. सो second quantity like cos minus z will be equals to cos z. You can verify in a similar manner only. Okay, just to use the relation between cos sine, these trigonometric functions, and the complex exponential function, and you will have your identity. Okay, then the third identity that we can have is that cos square z plus sine square z that is equals to 1. Okay. Now if you want to prove this, you just read the expression again. So we will have it as e to the power iota z plus e to the power minus iota z by 2, and we need to take the square of this plus e to the power iota z minus e to the power minus iota z over 2 iota, right, square. So it will be equals to, if you simplify this, then we will have e to the power 2 iota z plus 2 plus e to the power minus 2 iota z over 4. Okay, then plus we can write this is e to the power 2 iota z minus 2 plus e to the power minus 2 iota z, and we have the, here we have 4 and here we have minus 4. Okay, if we take the square of this, right, then that can be subtract from each other. So we will have e to the power 2 iota z plus 2 e to the power minus 2 iota z minus e to the power 2 iota z minus 2, this will be plus minus e to the power minus 2 iota z, right, over 4. So you can see this will be cancelled out by this one. It will be cancelled out by, this is 2 and here we must have 2. This is 2, it is plus 2 iota. Okay, so e to the power minus 2 iota z, then here we have e to the power in the negative, so it will be cancelled out by this. So we will have 4 over 4 and that is equals to 1, and hence the identity, right? And in a same way you can show that fourth one, if I want to identify sine z plus minus z2, then that will be equals to sine z1 cos z2. The same scenario, अगर प्लस साइन है then we have plus, अगर नेगेटिव साइन है तो नेगेटिव, then we have cos z1 sin z2. Then the fifth identity says that cos z1 प्लस माइनस z2, एंड जैसा हमने रियल में पढ़ा है सेम यहाँ पर cos z1 cos z2. Now if we have the plus sign then here we will have minus, अगर माइनस है तो यहाँ पर प्लस, ठीक है, and it will be equals to sin z1 sin z2. So these are some identities which are true in the complex analysis also. Likewise, if you take the double of argument, that is, if you want to identify sine 2z, then that is also equals to 2 sine z cos z. And likewise, we can write the cos 2 z, that is equals to cos square z minus sine square z. Just replace the sine 2z by the expression in complex exponential function and you will have this one. Okay, so these all identities can be achieved by just writing their complex exponential expressions. Okay,